everyone. Let me start with a little puzzle. Most materials shrink when cooled, right? Metals contract, rubber hardens, and liquids take up less space. But water, our life-giving liquid, refuses to obey this rule. Between 0 degrees Celsius and 4 degrees Celsius, water behaves in a completely opposite way. Instead of contracting when cooled, it actually expands. This unusual property is called the anomalous expansion of water. So, unlike ordinary substances, water becomes densest at 4 degrees Celsius. That's where it packs its molecules most tightly. Let's look closer at how water's density changes with temperature. At 4 degrees Celsius, water reaches its maximum density, 1 gram per cubic centimeter. But as you cool it further from 4 down to 0, the density actually decreases because the volume increases. Above 4 degrees, it behaves normally. Heating causes expansion, density decreases. As you can see in the diagram, the density versus temperature graph peaks at 4 degrees and then dips towards 0. That's why ice floats. It's less dense than liquid water. Now, what's really happening at the molecular level? When water cools below 4 degrees Celsius, its molecules begin arranging into an open hexagonal structure due to hydrogen bonding. This structure forces the molecules further apart, increasing the volume even as the temperature drops. At 0 degrees, this structure locks in to form solid ice, which is even less dense than liquid water. So the key culprit behind this strange behavior is hydrogen bonding, the same bonding that gives water many of its unique properties. Let's connect this to real life. Imagine a lake in a cold country during winter. As the temperature drops, the top layer cools down. The water at 4 degrees sinks, being the densest. But as water cools below 4, it becomes lighter and floats on top, eventually freezing at the surface. This thin ice layer insulates the deeper water, which remains at around 4 degrees Celsius. Fish and aquatic plants can continue to live beneath the frozen surface. Without anomalous expansion, entire lakes would freeze solid from top to bottom, wiping out aquatic life each winter. Thankfully, nature designed water with this extraordinary anomaly to safeguard life. Anomalous expansion has other fascinating consequences. Water pipes often burst in freezing regions because water expands as it turns to ice, exerting enormous pressure on the pipe walls. Icebergs float on oceans because ice is less dense, with about 1/9 of their volume above water. Even cold storage systems exploit the expansion of water during freezing. And in rivers and ponds, the frozen top acts as a protective blanket, allowing ecosystems to survive through harsh winters. So this anomaly is both a challenge, like bursting pipes, and a blessing, like preserving aquatic life. Let's solve a quick example to see this anomaly in numbers. Suppose we have 1,000 cubic centimeters of water at 4 degrees Celsius. Its density at this temperature is 1 gram per cubic centimeter, so the mass is 1,000 grams. Now, if we cool it to 0 degrees Celsius, the density drops to 0.9998 grams per cubic centimeter. Using the formula density equals mass divided by volume, we substitute 0.9998 equals 1,000 divided by volume. Rearranging, the volume equals 1,000 divided by 0.9998. That gives us 1,000.2 cubic centimeters. So the volume increases by 0.2 cubic centimeters, a tiny change for a beaker of water, but on the scale of lakes and rivers, it's massive. That's why freezing water can crack rocks and burst pipes. Let's recap the key ideas. Water expands when cooled from 4 degrees to 0 degrees Celsius, a property called anomalous expansion. Its density peaks at 4 degrees, then decreases as it cools further. The molecular reason is the hydrogen-bonded hexagonal structure that forms near freezing. This anomaly is critical for nature. It ensures aquatic life survives beneath ice, makes icebergs float, and explains why frozen water causes damage to pipes and rocks. So to sum up, anomalous expansion is one of nature's life-saving quirks. Without it, Earth's climate and ecosystems would look completely different. I hope this session gave you a clear and engaging picture of why water is so special. In our next lesson, We'll explore more wonders of heat and energy. See you there.